So as we closed out our session on Tuesday, we were reviewing the two different kinds of input data with respect to statistical analysis. Now there are different data types. When we talk about data types in a programming environment, we're talking about things like whether or not it's a whole number, an integer, or a number with a decimal point, a real number, or if it's a Boolean value like true or false, or 1 or 0, or on or off, or if it's string data, which means that there are letters and symbols, it's character data. In databases, you can have additional types of data, like currency data or date-time data, right? And that's not the kind of data, those aren't the data types we're talking about. When we talk about statistical analysis, we're not talking about data types in programming. We're talking about two broad categories of input data when we're doing statistics. And we said that there was discrete and continuous data. Discrete and continuous data. So what I'd like to do is just review that when we're working with continuous data, it often means that we're gathering information that's the result of measurements, and that there's like a finely graduated scale of incremental measures, like with height or mass or temperature. It's a value on a range of values or a continuum of values. It's not just one value or another. When we talk about discrete data, we're talking about data that falls into very cleanly and clearly defined categories, like whether an object is moving or at rest, or the months of the year, or the days of the week, or the species of an animal. Ordinarily, when we talk about the species of an animal, there could be different breeds of a species, but it's pretty clear that there's a difference between a bear and a mountain lion, right? There might be different breeds. There might be different breeds of dog, but when you're talking about a domesticated dog versus a fox, those are two different animals, right? And they can't breed in nature because they're different, right? So it's a class or a category. The sex of an animal, normally male and female, right? Any questions about the two different kinds of input data?
No.
Okay. So the reason that's important to understand is that when you're dealing with statistics, what I'd like to do is talk about the descriptive statistical analysis versus inferential statistical analysis. So if we have, just as we have two different kinds of data to collect and measure and analyze, there are two different kinds of statistical methods. So the two different kinds of data, that's one aspect of statistics. But when you look at that discipline by itself, there are two broad categories of methods that we use in statistics. And one is called descriptive and the other is called inferential. So descriptive statistical analysis is more concrete or absolute in terms of the results that are rendered. So these are methods that are centered on calculations with numbers, right? And you can graph results, and then the graphs reveal patterns, basic patterns in the numerical data, right? So these methods are all about the quantity. They quantify the precise characteristics of a single data set. So for example, the average of numerical values of selected fields or ranges of values, right? So when we calculate an average, we know what an average is. And if we have an average of values, let's take a series of let's take a series of numbers here. You can see my screen, yeah?
Yeah.
So this is basic math, yeah? And when we talk about the mean or the average, if we have 6 values and they're increasing by 10, 10, 20, 30, 40, 50, 60, and we add those together, that gives us a sum, right? So in simple terms, the sum of data's values would be an example of descriptive statistics, because it's a concrete thing. It's well defined and it's sensible. If you divide by the number of values to get the mean or average, you divide 210, the sum, by the count. So sum and count are descriptive statistical values. And when we take the first and divide by the second, we get the mean. So the mean is another descriptive statistical result. And measurements. Quite often, the data is distributed in a normal or typical manner. So the people that study statistics, they measure this stuff and they graph it, right? And they take the different values for a data set and they calculate how much those values will vary or deviate. And there's a predictable pattern, okay? In fact, when we have a completely normal distribution of data, statisticians say that we have a bell curve, and there's a standard deviation that is pretty predictable. In this case, a standard deviation for a normal distribution is 34.1% of the measurements. They're a little less than the average measurement, right? Or the average value. So if we're collecting data from something we're studying, there's an average value, and that's what's represented by the center line. And for a normal distribution, 34.1% of the data measurements are a little below average, and 34.1% are above the average. And that's referred to as a standard deviation. So this is a standard deviation less than the mean, and this is a standard deviation greater than the mean or average. Together, a normal distribution standard deviation represents 68.2% of the data points or measurements, right? Or values. That's for a normal distribution. In real life, there may be differences. When we take data values and we calculate standard deviation with the values that we measure, in real life, we get different results. And what we showed you here was how standard deviation is calculated. So first, what we do is we determine the mean or the average. So we take each of the values that we want to calculate the mean for, and we add them all together and we divide by the count of the number of values. This is something that most people already know. So 35 would be the average or mean of this distribution of values, okay? So this is just a hypothetical case with 6 values. Ordinarily, the larger the number of values and the more random the values are, the more you tend to look like something has a normal distribution of data when you're studying things in nature, right? And it's totally random. In this case, though, let's pretend that we have 6 measurements, right? So we collect data on 6 subjects in a population, a small population of objects, right? So we're studying 6 different things. Could be killer whales, it could be the size of fish in pounds, it could be the length of coral that grows each year, could be a variety of measurements, right? Are you with me so far?
Yeah, yeah, I understand that part very well.
Okay, so in order to calculate the standard deviation, there's a step that we have to take in between, where we first determine the difference between the data points or the data measures and the mean. And then we square them. And then we average the square of the difference between the mean and the actual data values. That's called the variance. So we're calculating how much each of the data points varies from the mean. Again, that's called variance. So here's what it looks like. I take this value and I use that to determine the difference for each of those values. And in this case, I get a negative value up to here because 30, if I take 10 minus 35, that's a minus 25. 20 minus 35 is a minus 15. 30 minus 35 is a minus 5. But then 40 minus 35 is a positive 5. 50 minus 35 is a positive 15. And then 60 is a positive 25, right? If I square those differences, what I get is this. I have 25 squared here, that's 625. I have 15 squared, that's where the 20 minus 35 is. Squared is 225. I have 5 squared, that's 25. I have, let's see, 40 minus 35 is 5. Squared is 25. 225 and 625. Now together that, if I add all of these up, I get 1750 and I divide by 6. That's called the variance. And if I take the square root of the variance, that gives me the standard deviation. I want you to notice that this standard deviation is half of a normal distribution we just talked about. So in this case, we would be drawing the bell curve much flatter. It would be like the blue bell curve. And if I drew the line here and here, it would only show 17.06% below the mean and 17.6% above the mean. And that would mean that instead of only having 13.1% here, I'd have something bigger. So instead of having a bell curve that's tall and wide, it would be more wide and less tall. Does that make sense?
Yeah, yeah.
Okay. Now, if I had a very large standard deviation, instead of having a 17.06 standard deviation, if I had a variance that was huge and or actually very small, I take that back. A variance that's very small, right? Because when you look at these values, there's quite a bit of difference between those values. But let's shrink the variation. Let's take a case where we shrink the variation and there isn't much of a difference anymore, right? What we would get when you finish calculating variance and then you go ahead and you calculate the standard deviation, what will happen is that you get a huge number. And so when you look at the normal distribution, instead of being so tall and so wide, kind of balanced, it would be more like the orange curve, right? So there isn't much variation. The distribution isn't normal. It's very different and it's all within a very tight range. So in that case, the standard deviation would be much greater than 34.1%. the standard deviation would be something like 42% less, and 42%, it would be like 42% more, 42% of the data values are greater than the mean, and 42% is less than the mean. So we have 84% of the population, 84% of the population within this very, let me see if I can slice this a little further. 84% of the population is within the first deviation or standard deviation, and then there's, if I slice again here, it's like I have a teeny tiny bit of I have just this part of the graph left on the right and the other side. I don't know if I'm making sense. The thing to remember is that when you have a larger standard deviation, you have a much taller curve, and you have less variation among the values for a data set. Does that make sense?
Yes, it does.
Yeah. Okay. So a plot of when you have a normal distribution and you plot it, that's one way to look at the distribution of data and how much it varies. But a really cool method, a graphical method to determine where most of the data is and how much it varies is something called a box and whisker plot. So that's the next assignment. What you'll do is you'll investigate some stuff online, and then you'll follow the steps in this PDF. So it explains how this is and how it works. And what we want you to be able to do is to use Excel to calculate some of the descriptive statistics for a data set. So I provide you with a data set. I want you to notice all the things we were talking about, right? The mean, the standard deviation, the variance, and then there's kurtosis and skewness, right? So if you have a certain data set, you can put in to Excel, it'll automatically calculate this stuff for you. And so the assignment walks you through how you calculate that to determine the descriptive statistics for a data set. So on the assignment itself, I actually give you,
When did I just start? Supposed to be over it on board, but it's taking a minute.
I actually give you the data to use. Can you see the descriptive data here? You see where it says descriptive CSV and then Whisker CSV?
Yeah, I do.
So I give you a set of scores, right? That's what this CSV file is. You don't have to put something in there. I give you the data to work the exercise with. And then what I want you to do is to create a whisker plot. So a box and whisker plot looks something like this. If you take the whisker data and you follow the steps in the reference document, what will happen is there's a quick walkthrough on how to create a horizontal box and whisker plot. And then you just follow the steps. Take the Whisker CSV, open it in Excel, and then this is what you'll end up with. If you look here,
Yeah.
what you get is a range of values. So when you're looking at this graph, here's the bottom value, the lowest value, here's the highest value, right? And the box is where most of the values are. Now, when you look at this whisker plot, are most of the values closer to the max value or closer to the min value? If most
they're
of the,
closer.
yeah, if most of the values are found within the box, and you're looking at this box and whisker diagram, so this is the box and those are supposed to be like the whiskers, right? Top and bottom. A lot of box and whisker plots have the whiskers left and right side, so they,
Yeah, I was about to say, but
yeah,
yeah, it's closer to the min value.
yeah. So if you look at the box where most of the values are, and you look at how this is arranged, the min value is here, the max value is there. Where are most of the values? Closer to the min, right? They're here. Now, if this chart were organized horizontally or in 90 degrees, you'd have the like a number line. You'd have the lowest value on the left, you'd have higher values on the right, like a number line. And then the box would be somewhere along that line. You could say, okay, most of the values are, well, they're evenly distributed between the lowest and the highest. In this case, you can tell most of my values fall closer to the minimum. And that's really important because what you want to do is you want to understand what's going on with the max numbers here. If most of my values are here, are these like rare exceptions? We would call them outliers, right? You'd say, wow, so, you know, I can tell that for this kind of data that's collected, this is the normal range of what we get. And every now and then we'll get some really high values. And then you can study, okay, why are we getting such really high values right here? So that's the value of a box and whisker plot. In here, in the exercise, when you click on the link, it actually shows you horizontal arrangements instead of vertical. But you're gonna create the vertical one like the one we show here. Okay?
Okay.
Do you have any questions about the assignment that we're performing?
No, I don't.